panel, we've got David and Leishan from the IT. There's myself, Paul, and we've also got Michael's going to be keeping track of any questions and responding to chat as we go through. Michael's not got his video on at the moment, but he is listening in the background. And we've got the most important person, of course, tonight is our speaker, James Buchanan. So he'll be doing the presentation. Yeah, as we go through, if you can turn your mics off and your videos off whilst we actually deliver the presentation, then it stops any distraction and any background noises coming through. If you also, as we go through, if there are any questions that come to mind, as I say, Michael will be monitoring the chat, so put any questions into the chat. If the questions for our speaker, Michael will read those out at the end of the presentation for James to answer. Right, so we'll make a start then. So James Buchanan from the United Kingdom Atomic Energy Authority is our speaker tonight. James has a DPhil in experimental particle physics from Oxford, having previously worked in the Atlas experiment at the Large Hadron Collider. He now works as a computational physicist at the United Kingdom Atomic Energy Authority and in the Advanced Computing Department, which is very much the aspect which we're going to be listening to tonight. So with that, I'll hand over to James to take you through the story for tonight.
Oh, thank you very much for the nice introduction, and thank you for the opportunity to speak. I'll just share my slides. Okay. Can you see the slides? Is that okay?
Yep, we can see those.
Oh, okay. Yes, so as Paul said, I'm from the United Kingdom Atomic Energy Authority. We're effectively the UK's fusion energy research organisation. And so today I'm going to talk a bit about what fusion is, why we think it's important, what the kind of current state of the art is, what some of the kind of outstanding challenges that we're working on addressing are, and then towards the end about how kind of modern computing and data science techniques are starting to influence how fusion research is done. So in terms of kind of background context, the context is that we need to reduce our carbon emissions in order to prevent climate change, basically. So at the risk of, singing to the choir, we're very reliant on fossil fuels for all of our energy. Fossil fuels produce carbon dioxide, and carbon dioxide is a greenhouse gas, which means that when the Earth radiates heat into space, the carbon dioxide will reflect some of that heat back to the Earth. And so if you add more carbon dioxide, you heat up the surface of the Earth. And what I think most people know about this, I think a lot of people don't know how long we have known about this. So the greenhouse effect was first predicted by a Swedish chemist called Arrhenius before the turn of the last century. So this little newspaper clipping talks about his prediction. So Arrhenius holds that the combustion of coal by civilized man is gradually warming the atmosphere, so that in the course of a few cycles of 10,000 years, the Earth will be baked in a temperature close to the boiling point. He bases his theory on the accumulation of carbonic acid in the atmosphere, which acts as a glass in concentrating and refracting the heat of the sun. So it's a somewhat dated description, but for over 100 years ago, it's not bad. This is a picture of the famous American astronomer Carl Sagan testifying to Congress about the greenhouse effect in 1985, and this is available on YouTube. So It's only about 16 or 17 minutes long, but it's quite compelling, and pretty much everything he says in 1985 is still true today. So, you know, it's been something that's been talked about for, you know, quite some time. So what is the current kind of state of affairs with climate change? So these plots are taken from one of the recent IPCC reports. They produce various reports, and they produce these summary for policymakers documents that kind of give high-level overviews. And this one on the left basically shows the temperature deviation from the kind of pre-industrial average over time. They take kind of 1850 to 1900 as a baseline, and you can see that since the start of the industrial era, there's been a really rapid increase in surface temperature. The plot on the right is basically trying to justify that this is down to human changes, so anthropogenic carbon dioxide emissions. So you can basically model the evolution of the climate system, and if you ignore the human contributions to carbon dioxide emissions, you don't see this rapid uptick in temperature. And then when you do include it, you get something that matches observations. So this is basically, you know, part of the argument that these rapid temperature changes are being caused by us, by our burning of fossil fuels and producing carbon dioxide. These plots are a little bit out of date now, so they're from 2019 from the US Energy and Information Administration. They're basically showing how energy consumption is projected to change over the next few decades. So this plot on the top is basically showing you that energy consumption is expected to increase fairly linearly over the next few decades, largely driven by industrialization and development in countries in Asia. So the OECD countries' consumption of energy is predicted to be fairly constant, but the total energy consumption is predicted to continue to go up. They predict that there will be a fairly strong uptake of renewables over the next few decades, which is great. However, the fact that the total consumed energy is also expected to go up by a lot means that even though renewables will become a greater share of the overall energy portfolio, the total amount of fossil fuels being burned is still actually predicted to increase somewhat. So, you know, and climate change only really cares about the total amount of CO2 that you're putting out. So as I said, this is slightly old. I think the situation has probably improved a bit over the last few years. So there was some articles in the BBC earlier this year suggesting that this will actually be the first year that the total CO2 from electricity production will go down slightly. So it's, you know, the situation is still getting worse, but it's not getting worse faster. So, you know, some silver lining there, I suppose. So basically we need alternative energy sources that don't produce carbon dioxide if we want to limit and mitigate this, you know, raising surface temperature. And so this brings us on to fusion. So fusion is something we've understood for about the last 100 years, and it's basically the power source for the sun and the stars. So it was first realized in 1920 by the astronomer Arthur Stanley Edison that the power source for the sun was nuclear. Before that, there was an argument going on about whether, like, why the sun burns, and people thought that it might be due to gravitational collapse. So as the sun collapses in under its own gravity, you change gravitational potential energy to kinetic energy and heat, and that might be why the sun burns. But it was kind of realized that that can't account for the amount of energy that the sun produces. And so Edison wrote, "A star is drawing on some vast reservoir of energy by means unknown to us. This reservoir can scarcely be other than the subatomic energy, which it is known exists abundantly in all matter. We sometimes dream that man will one day learn how to release it and use it for his service. The store is well nigh inexhaustible if only it could be tapped." So people have dreamed about being able to harness fusion energy for over 100 years now. So how does it work? So fusion is sort of the opposite process to more conventional nuclear power. So in conventional nuclear, you take large nuclei like uranium, thorium, and split them. But you can also take very small nuclei and fuse them and release energy. And so this is what we do. When you look at these processes, you find that the sum of the masses of the products of the reaction is slightly smaller than the sum of the masses of the inputs. And that mass difference is converted into energy by Einstein's famous E equals mc squared. So I think this is the only equation I've put in this talk. So we could try and replicate the reaction chain that happens in the sun. It's something called the PP chain, and it basically converts 4 protons, so 4 hydrogen, into helium. But the actual reaction that the sun uses is actually very, very slow. It doesn't have a high reaction rate. The sun produces a lot of energy by virtue of being very, very big, but that's not an option we have for reactors on Earth. So we have to do something a bit different. Fortunately, there are alternative fusion reactions available that have higher rates of reaction. And the one that we typically use and that is used in most fusion concepts is this reaction, which is called the DT reaction. So in this reaction, you take deuterium and tritium as inputs and produce helium and a neutron as outputs. If you're unfamiliar with deuterium and tritium, then effectively they're heavier siblings of normal hydrogen. So normal hydrogen, the nucleus of normal hydrogen is basically just a single proton, which in this diagram is just represented by these red balls. Deuterium has a proton and a neutron, and tritium has a proton and 2 neutrons. So they're just heavier variants of hydrogen. So what are the benefits? So as we kind of discussed, it's low carbon. That reaction doesn't produce any carbon. So the carbon footprint of fusion comes just from the construction of the reactor and mining and so on and so forth. It's safe. It doesn't work, as we'll come on to, it doesn't work like conventional nuclear where you control a chain reaction. There's no chain reaction. In fact, it's very hard to maintain the conditions needed for fusion. So if you had any kind of fault or loss of power or anything that disturbed a fusion reactor, it would just stop doing anything. It would stop working. You might damage the reactor, but you certainly wouldn't have any kind of more serious consequences. It's reliable. It produces what we refer to as baseload energy. So baseload energy is effectively just energy that can be turned on and off to meet demand. It's sustainable in the sense that there is really abundant fuel. So deuterium, there's millions of years worth of deuterium present in seawater. So there's just some fraction of the hydrogen in water is deuterium, and it's quite a small fraction, but there's a lot of water. So it's also very energy efficient. And by that, I mean that you can provide power with a comparatively small amount of massive fuel. So if you wanted to power one person's energy use for 60 years, you could either do that with 16,000 wheelbarrows of coal, or you could use a bathtub of water and 2 laptop batteries and do fusion. So basically extract the deuterium out of 1 bathtub of water. I'll come back a little bit later to why you need the laptop batteries, because that's a little bit more nuanced, but the deuterium is in the water. So this all sounds super rosy, but so what's the catch? The catch is that it's just extremely difficult to do this, as you might have guessed. So fusion reactions effectively rely on the nuclear strong force. So the nuclear strong force is one of the kind of 4 fundamental interactions in the universe, and it's the interaction that binds the nuclei together. It's very short range. For it to actually affect things, they have nucleons, they have to be extremely close, basically touching each other. That's challenging because nuclei contain protons, which are positively charged, and like charges repel, which means getting the nuclei very close together means fighting against the electrostatic repulsion that they have, which is difficult. You can do that by making the fuel species move very, very, very quickly, so they have enough kinetic energy to overcome that repulsion. And that means making the fuel very, very, very hot. How hot? About 150 million degrees of hot. That's a very big number and probably doesn't mean much on its own. So for reference, that's 10 times hotter than the core of the sun. So this is obviously quite hard. And when you make something that hot, you produce what's called a plasma. So a plasma is it's a gas where there's so much energy available that you strip all of the electrons off the nuclei, and you end up with a kind of soup of charged particles that all moves together. So you can kind of think of it like a fluid that can carry electrical currents. Plasmas are kind of ubiquitous in nature. They exist all over the place. Auroras are plasmas used in neon signs. Lightning is a plasma. As we've established, the sun is itself a plasma. Plasmas used in industrial processes like welding, and maybe most relevantly for this meeting, they're also used for etching silicon wafers. And there's various others, and these are all very different kinds of plasma. So there's quite a wide parameter space in terms of densities and temperatures of plasmas, but these are all plasmas. So it really is one of the most common states of matter, despite being quite unfamiliar to most people. Now the question is, how do we actually confine this to build a reactor? You know, we've got this gas, this plasma that's 150 million degrees hot. How do you contain something like that? If you just put it in a box, it would melt the wall and then cool down and not be very useful. And the answer is we can use magnetic fields. So in order to understand this, I'm just going to give you a little bit of background about how charged particles behave in magnetic fields. And the short story is they basically follow them. So if you have a magnetic field, the charged particles will just sort of move along it. The slightly longer story is, as shown in this diagram, that magnetic fields tend to bend the trajectories of charged particles into these kind of helices. But in a fusion reactor, the radii of these little helical motions are very, very, very small. So really, you can think of the charged particle as just pinned to one of these magnetic field lines, and it's just sort of wibbling along it. The upshot of that is that if you can create a magnetic field geometry where the magnetic field closes on itself in a circle, then the charged particles and consequently the plasma as a whole will just sort of follow the magnetic field lines and remain confined. So that's the basic trick. So how do you use that to make a reactor? Well, you do that like this. So this is called a tokamak, and this is the variant of magnetic confinement fusion that we research at UKEA. And it was first developed in the Soviet Union, actually. And the core, I'll kind of talk through the core components. So probably the most important things are these teal coils. So these are what are called toroidal field coils. And they basically create a circular magnetic field, as shown by these teal arrows. So it's just a magnetic field that kind of goes round in circles through the middle of the coils. Now, it turns out that when you hack through all the kind of detail of this, that on its own is not quite good enough to get the level of confinement that you need for fusion to work. And you need to slightly change the geometry of the field by adding another magnetic field that kind of goes in the other direction around this donut. We call this a poloidal field. And you can generate this other field by driving a current through the plasma. So that's represented by this green line. So you create a plasma current, and this plasma current will create this other field component. The plasma current is itself created by transformer action. So basically, the other main component of a tokamak is this big electromagnet down the middle. And when you change the current through this electromagnet, the transformer action results in driving a current through the plasma. And so these two components together, these magnetic field coils and this solenoid, allow you to create this slightly complicated magnetic field geometry that allows you to confine the plasma. The last component here are these grey coils, and these are basically used to help shape the plasma, so they can squish it or pull it out or, you know, move it up and down, but they basically allow you to control it. And that's the basic gist of how a tokamak works. So that's a schematic. What does it look like in reality? So this is a shot inside the JET tokamak at Cullen. So JET stands for the Joint European Torus. So this was a kind of joint European experiment. It's still currently the largest tokamak in the world, and it set a new world record for fusion power in 2021. Is, however, about to reach the end of its life, so it will do its last deuterium-tritium campaign later this year, and then at the end of this year it will be decommissioned. Well, start being decommissioned. That will actually take a while, but for the time being it's still the largest, and it's also the only one that currently can do deuterium-tritium fusion. This little video basically shows is a pulse, so an actual experiment on JET, so I'll just run that. You should be able to hear the sound as well, hopefully. There you go. So that's what a shot looks like on JET. And when it's running, it's basically the hottest place in the solar system, which people don't expect of rural Oxfordshire. So that's kind of gives you a sense of how we do fusion. There are other magnetic confinement devices that other laboratories explore as well, and I can talk about some of them in the Q&A if that's of interest. And there's also some entirely different fusion concepts that people explore too, but I think the tokamaks are still really the most mature concept and probably the most researched globally. So now I'll move on to talking about what some of the kind of main obstacles and challenges facing fusion research at the moment are. And the first one is around exhaust. So you might have noticed in that previous video that there was a region at the kind of bottom of the video that was glowing very, very brightly. And this is what's called the diverter region. It's basically the exhaust region of the device. So I kind of painted this picture before about particles being stuck on magnetic field lines and just moving nicely around the device. But in reality, there are mechanisms like collisions and turbulence that cause transport of particles and heat out of the device. So the plasma kind of will gradually move out of the reactor towards the raw wall, and we basically use the magnetic field to then guide it down into this exhaust region where we can put high thermal conductivity materials and cooling pipes and other things. And the heat flux in this area can be very large. So on JET, it can be up to 50 megawatts per square meter, which is comparable to the heat flux that a space shuttle re-entering the atmosphere has. And so a big challenge is around how to design these diverter structures such that they'll be able to tolerate conditions in real reactors whilst requiring minimal maintenance, because the more you have to maintain and replace components, the more downtime your reactor will have, and the less, and that hurts the economics. So really, we want these to be able to last as long as possible. And this is one of the main goals of the other reactor we have on site, which is called MAST upgrade. So MAST stands for mega amp spherical tokamak. It's a smaller device than JET, and it's a slightly different. It's still a tokamak, but it's kind of compressed, so it looks less like a donut and more like a sphere. And one of the key points about it is that it has a novel diverter concept called a super X diverter. And basically in the super X diverter, well, I've actually got a video of it in a second, but you kind of use additional coils to kind of expand the plasma out into this kind of cavern region under the device. And this allows the plasma to travel a much larger distance before it hits the wall, and that allows it to cool down more. And MasterU is now in the middle of its second campaign, and one of the key results from the first campaign was showing that this super X diverter does give quite a large decrease in the peak heat flux on the wall compared to a conventional diverter. So this is kind of a quite promising result, and there's a little visualization showing sort of what this looks like. Is this doing something? Oh, it is. Yeah, so here you can see the cross-section inside mast and one of these plasmas, and as you can see, the cross-section looks closer to circular. And these are some of the particles in the plasma whizzing around the device, and as they gradually move outwards, they kind of wind round the device into this diverter region. And because they're going around the device as well as moving, the distance that they will travel to get to the target plate is actually quite long. There are other advantages to having this kind of structure. You can puff neutral gas into this region to help the plasma cool down. And also, when the plasma does interact with the wall, it can cause material sputtering. And you really want to keep that separated from the core of the plasma, because you don't want wall impurities contaminating the core of the plasma. So there's a few reasons why this is kind of a promising structure, but still being able to handle the heat exhaust of the fusion reactors is a big challenge, and there's other things that people are doing to try and explore how to deal with that. The second challenge is around plasma stability. So I kind of mentioned before that a plasma is sort of like an electrically conductive fluid, and you can kind of think of, yeah, if you can think of confining it as somehow similar to like having a balloon filled with fluid and trying to compress it. It will try and escape out of any gaps, and plasmas are similarly difficult to deal with. And there are a zoo of different kinds of instabilities that can exist in plasmas that can have negative impacts on the overall performance of your reactor. One example is something called an edge localized mode, and it's kind of the tokamak equivalent of a solar flare. There's a little video here of MAST, so before it was upgraded, and you'll be able to see some of these instabilities in a minute in this video. These edge localized modes, they occur when the pressure at the edge of the plasma, when the pressure gradient there becomes too large, and they eject a lot of heat and particles into the wall in a single go. So you're able to see one now. There you go. So that bright flash, that's one of these instabilities, and they happen periodically. So there's another one now. Yeah, so these things, yeah, these filamentary eruptions, they deposit a lot of power in a very short amount of time on the walls of the device, and so consequently they can be quite problematic. For smaller devices like MAST, there's not enough stored energy in the reactor for it to be a real problem, but for larger reactors where there's a lot of stored energy, these things could be really problematic and cause material damage in the reactor. So there's a lot of effort around trying to find strategies for controlling and mitigating the impact of these kinds of instabilities. And this is another one of the kind of research topics that's quite important in MAST. Third challenge is around advanced materials. So while one strategy for kind of mitigating the exhaust problem is to build reactor designs that minimize the actual heat deposition onto the wall, the other strategy is to try and develop materials that have better thermal properties, so higher melting points, better thermal conductivity. And the other particular issue to fusion reactors is the radiation environment. So I kind of mentioned at the start that the deuterium-tritium reaction produces a neutron. That neutron is neutral, and so it doesn't see the confining magnetic field. It basically pings out of the device and hits the wall, and it's very energetic. So these neutrons can basically cause quite complicated material damage to the wall. So this image on the top right is what's called a collision cascade in tungsten. So an energetic particle has been fired into the tungsten lattice. It's hit one of the nuclei, displaced it, that's hit other atoms in the crystal lattice and caused this kind of cascade of dislocations. So these neutrons can cause really complicated material damage, and that can cause swelling, embrittlement, and other, problematic changes to the properties of the materials. And so we really need to understand both how to design new materials that have good thermal and radiation properties, and be able to understand how this kind of damage affects the properties of the materials. Yeah, in fusion, we typically use a measure of radiation damage called displacements per atom. And basically what this means is how many times each atom in the material will get kicked off of its default lattice position. And in a real fusion environment, that's expected to be about 20 to 50. So to give you a sense of how challenging this is, it's trying to understand what happens to materials if you kick every single atom in them 20 times. So the fourth one is around handling and breeding of tritium. So I kind of glossed over the tritium part of the fueling earlier and talked more about deuterium. Tritium is much more complicated because firstly, it's not naturally occurring, and secondly, it's radioactive. So the radioactivity means there's a lot of challenges around handling of tritium from a regulatory perspective. But the fact that it's not naturally occurring means we need to be able to create it. And you can actually do that inside the reactor using the neutron that's produced. So I also mentioned earlier that you needed lithium to do fusion. This was the the batteries thing that I kind of mentioned earlier. And the reason you need lithium is to create the tritium. So lithium reacts with neutrons and will split into helium and tritium. And the tritium can then be used inside the reactor. So what you can do is you can line the walls of your reactor with lithium, and then the neutrons that are produced in the reaction will react with the lithium to produce tritium, which you can then feed back in. And this diagram makes that look not particularly complicated, but in reality, these structures, which we refer to as breeder blankets, are very, very complicated. And it's a big engineering challenge to be able to design these things. You need shielding for the neutrons. You need to be able to extract the tritium that's generated. There needs to be cooling structures in these things. So being able to design these and ensure that they will produce sufficient tritium to produce a steady state process is well, it's a big challenge. We have a dedicated facility that only opened a couple of years ago called HEAT, which is around exploring technologies related to tritium handling and tritium research and development. So the H3 is hydrogen 3, which is basically what tritium is. So it's a clever pun. But yeah, so this recently opened and focuses on tritium research. The last challenge I'll talk about is around remote handling. So as discussed, the walls of the reactor get bombarded with these neutrons, and this causes material damage. It will also make the walls radioactive over time. Another challenge for JET particularly is that the first wall's made of beryllium, which is toxic. And so basically the interior of a fusion reactor will be an inhospitable environment for humans. However, you still need to be able to do maintenance. We'll need to be able to replace things, change things. And so you need a strategy for being able to perform remote maintenance. JET has a remote maintenance solution, which is called Mascot. And here's a little video of Mascot happily replacing some tiles around diverter. This is not a robot, it's actually a remote manipulator. So there's a person in a room nearby, this person, who has these replica arms that allow them to control the arms on the Mascot. And these people have to undergo a lot of training to be able to do this. And part of their final exam involves getting the Mascot to play Jenga. And this thing has what's called haptic feedback. So that basically means that the operator can sense the resistance to movement of the device. So it's scaled, but it basically they feel something like what Mascot's feeling when it's operating. The kind of knowledge of remote handling that was developed during the operation of JET has been kind of spun out into a dedicated institution for robotics in challenging environments, which we call RACE. And they still focus on development of maintenance strategies for fusion reactors, but they also work a lot with other industries where there are inhospitable environments to humans. So this includes deep sea exploration, space exploration, conventional nuclear. So basically the gist is that there's a lot of different cross-disciplinary challenges in fusion, ranging from plasma physics, materials science, robotics, and computing underpins a lot of these things. I'll come on to that. Just a quick image of what our site looks like. So UKE is based in Oxfordshire, a place called Culham, which is between Oxford and Reading. And this is a recent picture of our site. So JET is over here in this white building. MAST is over here. The materials research facility we have, which do experimental testing of samples of irradiated materials, is here. The robotics building is over here. We actually have, you can't see it on this picture, but we have a apprenticeship building. So this is Oxford Advanced Skills, but it's basically for apprentices. So we've had an engineering apprentice scheme for a long time, but we have actually recently started taking computing apprentices as well. So they join us at 18 after their A-levels, and they do a degree in digital technology solutions with Warwick, and then block release and work 80% of their time on site with us. Tritium facility is here, and we also have various scientific tenant companies. A little bit about the future path. So as I said, JET is reaching the end of its lifetime after almost 40 years of operation at the end of this year. And part of the reason for that is that the next generation device, ITER, which is being built in the south of France, is expected to come online towards the end of this decade. This kind of shows the two side by side. ITER is another kind of experimental reactor, but it's expected to produce 500 megawatts of thermal power and a Q of 10. So Q is effectively a measure of how much energy you're getting out for how much energy you're putting in. So this is expected to produce 10 times more power out than goes into it. But it's worth noting it is an experiment. It's not a power station, so it doesn't have an electrical back end. It's not going to produce electricity. This is a fairly recent image of the site in Cadarache in France. So it's near Marseille, about an hour north. And yeah, this is just kind of gives you a sense of the progress in construction. In the UK, we have our own dedicated programme for design of a future power station based on the spherical tokamak concept, so similar to MAST. And basically, we're aiming to develop a prototype power plant based on the spherical tokamak concept by 2040. So an actual power plant that will be connected to the grid and produce electricity. And recent news from that is that a site has been selected for this, a place called West Burton, which is near Sheffield. Yeah. So this kind of is just a summary of that roadmap. So at the moment we have MAST and JET. Towards the end of this decade, ITER should come online. We'll get a lot of valuable information about reactor grade plasmas from ITER. In 2040, we hope to have STEP up and running in the UK based on the spherical tokamak concept. And then in the 2050s, there's a conventional prototype, a conventional tokamak prototype power plant called DEMO, which is kind of European design, is expected to be built. So this is kind of the future tokamak roadmap. So how can computing help with all of this? So as I said before, I think computing is a thread that can have impact across all of these different disciplines and is already doing so. And there's a lot of advances in modern computing, a lot of areas where computing can have bearing on fusion research. And I've just listed some of them here. So systems and control is extremely important. We're trying to control a very temperamental plasma. And so advances in control and computation for control is very relevant. We're interested in data systems and digital threads. High performance computing for simulation is very important, and I'll talk a bit about that. Data analytics and artificial intelligence are very important for being able to extract information from the experiments we do and the simulations we run. And advanced visualization helps scientists extract information from the results of their simulations and experiments. And I'll talk about some of these things. It won't be exhaustive, partly because of time and partly because of my own limited knowledge, but hopefully I'll be able to show you a few interesting examples. So what's the top level narrative? So the main headline is that it's too costly to use a traditional engineering, design, build, test methodology for building fusion reactors. So a lot of systems, you can make a design, you can build it, you can test how it works and learn from it, and then feed that back through to a new design and kind of repeat this process. But for something as big and expensive as something like STEP, you can't do that. We also are missing information about reactor conditions that we would ideally like to be able to use in making a design. So we haven't yet produced reactor grade plasmas. ITER will do that, but ITER will not be running until, well, it won't be finished construction until later this decade, and it probably won't be producing burning plasmas until the 30s. We haven't got material samples exposed to the kind of high neutron fluxes that they will be exposed to in a real fusion reactor, and we don't have real components subject to the kinds of thermomechanical and electromagnetic loads that they'd be exposed to in a fusion reactor. So we're very much at the mercy of simulation for a lot of these things. And ideally, we want to have robust digital twins that we can use for optimization and design. These need to be fast, they need to be accurate, and they need to be actionable, which means they need to be equipped with uncertainty quantification so that we can trust the results that they produce. Now, this kind of nice idealized vision is very difficult because, as I've hopefully conveyed to you in the rest of this talk, there's a wealth of different physics involved in a fusion reactor operating on different spatial and temporal scales, and there's a lot of coupling between different systems. So being able to do this would require a lot of compute resources. Fortunately for us, the march of high performance computing continues. And more compute power is becoming available to scientists, which is great. This plot on the right is probably familiar to people. It basically shows the status of the top 500. So the yellow curve is the 500th computer in the top 500 list, so the one right at the bottom. The red one is the fastest supercomputer in the world, and the blue curve is kind of the sum of the compute power in blocks of all of the computers in the top 500 list. And I'm kind of missing some points here, so there should be one more point just here from June 2022, which is the Frontier supercomputer, which was the first computer to break the exascale barrier. So it got 1.102 exaflops on the impact benchmarks. And this is a photograph I took at the ISC of one of the blades from Frontier, and you can see the GPUs. So one of the difficulties here is that supercomputers are becoming more heterogeneous, and so it's becoming increasingly hard to easily exploit the compute power that they offer. The UK's response to that, well, one of the UK's responses to that is a program called Excalibur. So this stands for exascale algorithms, exascale and computing algorithms and infrastructures benefiting UK research. So this is a kind of a research program led by the Met Office to explore software, algorithms and tools to allow exploitation of next generation supercomputers. And there are two priority use cases. So the first one is the weather and climate use case for the Met Office, but the second is around fusion simulation. And it's centered on the development of a code called Neptune, which is targeting simulation of the edge and diverter regions of the plasma. So this simulation is aimed at being able to optimize diverter design, which is this exhaust region that I talked about earlier, and enable control of the plasma in this region. Yeah, and so this code is being developed to target, you know, modern supercomputers like Frontier, which are predominantly GPU based. While Neptune is kind of one of the flagship simulation development programs we have at the moment, simulation is used ubiquitously across Fusion for a wealth of different tasks. And I've just shown images of a few in this slide. So this image on the top left is actually a code that I personally have worked on. It's called Locust. And so basically what's being shown here is simulations of some of the heating sources of the plasma. So I talked before about how you can find plasmas using magnetic fields. I didn't say much about how you heat them. And one of the ways you can do that is using basically gigantic particle accelerators that fire beams of energetic particles into the plasma. And you care about knowing how effectively they heat the plasma, what the deposition profiles of heat in the plasma are, and also importantly, how many of those energetic particles that you fire in don't go into the plasma and actually hit the wall. And if they do hit the wall, do they cause localized heating, and is that a problem? And Locust is basically a GPU code that allows you to simulate the injection of these particles and calculate the kind of heat deposition profiles on the wall components, which is important for reactor design. This bottom left image shows a simulation of turbulence inside the core of the plasma. So a lot of the heat transport in the plasmas is driven by complex turbulent structures. I'll say a bit more about this in the next few slides, but understanding this is very important because a lot of the performance of a particular plasma scenario will be governed by how much heat transport there is in the plasma. So, and that comes down to understanding the kinds of turbulence that are present. So you can see in this image, there are these little turbulent vortices inside the plasma, and these are very effective at transporting heat. So ideally, we want to kind of find scenarios where there's minimal turbulent transport of heat, because that will allow us to get high temperatures inside the plasma, which will give good fusion performance. These simulations, however, are very expensive, particularly simulations of the whole of the plasma, like this one. The simulation on the right is a simulation of microstructure that's developed inside tungsten due to irradiation. So I showed you before an image of a single neutron impacting on tungsten and producing a kind of defect cascade. when you subject these materials to large fluences of impacting energetic particles, you develop these very complicated and quite pretty microstructures. So these kind of diffuse blue dots are vacancies in the material. So they're where an atom has been removed from its lattice. These red dots are what are called interstitials. So they're atoms that have been added. And the green lines are what are called dislocation lines. So they're where the interstitials have caused like dislocations inside the material. And you get these very complicated dislocation structures. And these kinds of simulations allow scientists to help understand, well, the kinds of changes in material properties that these kinds of large fluences of neutron radiation will produce. So this is kind of the microscale. This image on the top right is showing kind of component scale simulation. So ideally, we'd like to be able to couple this kind of information to these larger scale component simulations. These used kind of assumed radiation swelling profiles, but basically they allow you to predict how components will swell and deform under a radiation damage. And that's important because it allows you to make design decisions. So this component is meant to be a breeder blanket, and these are meant to be coolant channels. But what these two simulations are showing is that if you change the structure of the interior coolant channels, you can actually reduce the maximum radiation-induced stress, which means you have lower likelihood of cracking and deformation. So this is just kind of a demonstration of how we can use finite element software to inform the way we design components. But ideally, you'd like to be able to couple all of these things together into, digital twins that model the combined plasma and reactor system. But each of these things is individually very expensive, so that's quite a big challenge. As I said, despite all of the available compute resources, a lot of simulations are very expensive and so much so that they can't be routinely used inside design workflows. One way of dealing with that is to generate what are called surrogate models. So surrogate model is a kind of inexpensive statistical model that's trained on an expensive simulation or some experimental data. Typically, this is done using machine learning tools like neural networks and Gaussian processes. So to kind of give you a bit of an example of what this looks like in practice, suppose you had some coupled workflow that you wanted to explore to use for design optimization. And suppose one component in that workflow was very expensive and was basically the bottleneck for this workflow. Instead of using this slow workflow to do your design optimization, you could pull out this expensive simulation, study it in isolation by doing a kind of a simulation campaign to generate a training data set, and then train some machine learning model on that training data set. And if you can show that that validates well, you can then use that machine learning model in the place of the expensive simulation to produce a fast workflow that you can then do design optimization with. And that's good. There are various situations where this kind of surrogate modeling approach is being used to try and accelerate simulation. And one area is this situation of trying to understand turbulence inside the plasma. So as I said earlier, a lot of the heat transport inside the core is driven by turbulence. Here's a little animation of some turbulence. This is actually fluid turbulence rather than plasma turbulence. So this is a fluid column that's being heated from one side, and it's driving turbulent structures inside the fluid. I just think it's quite pretty. Turbulence in plasmas is typically driven when a critical gradient in something like the temperature is exceeded inside the plasma. So there's this little cartoon which kind of gives you a heuristic idea. So the x-axis here might be something like the electron temperature gradient. And at low temperature gradients, you don't get any turbulence and all is well. and then above some critical gradient, you start to drive turbulence, and so this causes a rapid increase in the heat flux, which prevents you from being able to further raise your temperature. If we want to be able to predict how a reactor plasma will evolve, we need to be able to predict the heat and particle fluxes that these kinds of turbulence structures produce, and use them inside integrated modeling frameworks. One code that allows you to do this is something called qualities. There's various codes that do this, it's just one example. And if you want to do time evolving simulations of the plasma in the reactor, this code has to be called every time step at every point inside the plasma to tell you what the heat flux is. So it can end up being called thousands of times per second in a plasma simulation. And as a result, it's often a bottleneck for these kinds of integrated simulations. And so consequently, if we can build a surrogate model of qualities, we should be able to accelerate scenario modeling for plasmas. And this is being done by a group in the Netherlands called DIFFER, using a feed-forward neural network. So to do this, they generated 30 million training points across the 10-dimensional parameter space using qualities. And this took them 1.3 million CPU hours. And they used that to train a neural network. The architecture shown here. For the sake of time, I might not talk too much about the particular architecture that they chose now, but if you want to, I can talk about it more in the Q&A, because they used some physical insight in the way that they designed the architecture to help it be suitable for the particular problem. When they use this neural network, the coupled simulation workflow reduced from 3.6 hours per simulation to around 15 seconds. So this is, really quite dramatic improvement in simulation time to do this kind of scenario modeling exercise. The paper that they wrote on this is down here, and it shows some benchmark cases on JET. This shows one where the deviation in the predicted plasma profiles is only 5% worse compared with the full fidelity simulations. And this is fairly typical. Some of the worst cases that they looked at had about 15% deviation, but for such a dramatic speed up, this is very good. And so there's a lot of work going on across the community in exploring building these kinds of surrogates. Some of the work that I'm involved in is doing trying to build similar surrogates but for different kinds of turbulence using Gaussian processes. So if you're not familiar with Gaussian processes, they're a kind of statistical tool which allow you to kind of define a probability distribution over possible functions that match data that you have. They're fairly easy to use, and they importantly have an intrinsic measure of uncertainty, which is very important for surrogate modeling in scientific disciplines. We want to know how accurate and how much we can trust these kinds of surrogate models that we're building. And Gaussian processes are also very good for sparse data. And for the particular kinds of turbulence we're looking at, the simulations that you have to run to predict their behavior are much more expensive than qualities is. So we won't be able to generate a data set of the same size that the people at DIFFER did. So consequently, we thought that a Gaussian process might be a more suitable tool than a neural network. So that's all I'm going to say about surrogate modeling. I'll move on to some of the ways in which AI is being used to help make inferences from data rather than simulation. And one of the most important areas in fusion where that's the case is around something called disruption prediction. So disruptions are large-scale plasma instabilities. They're much worse than the ELMs that I talked about earlier, so much so that they don't just negatively impact the performance, they actually result in the loss of the shot. So all of the energy that's stored in the plasma is lost and deposited onto the wall all at once. And these are so bad that future reactors will not be able to have them. We need to prevent these things from happening. So it's very important that we be able to predict when they're going to happen, avoid them. And the sooner you can predict that they're going to happen, the less dramatic the intervention you have to make is. So being able to predict them well ahead of time is really beneficial, because it will mean that we can take less severe action and prevent reactor downtime, which again kind of feeds into the economics. We don't have any first principles models available for predicting these things, so we're very much reliant on experimental data. And so recent work done at Princeton Plasma Physics Laboratory has looked at using recurrent neural networks to predict when disruptions are going to happen. So they basically built experimental databases and labeled whether they were disruptive or not, and then use the experimental profiles, so things like the temperature and density inside the reactor from experimental measurements, to train a LSTM, so this is a kind of recurrent neural network, to predict effectively a measure of the likelihood of the plasma to disrupt. And you can use this disruptivity measure to set an alarm, at which point you say, I think a disruption is going to happen and I'm going to take some kind of remedial action. They looked at a couple of, well, they basically looked at JET, and they also looked at a reactor called D3D, which is in San Diego in the States. And they got pretty good results with doing this. So most notably, they managed to train on D3D and still get very good results transferring that information to JET. They got even better results if they allowed the training set to have a small sample of JET data, which they referred to as a glimpse. So this is meant to kind of reflect the situation we have, where we want to be able to predict disruptions on future reactors using data that we have from current experiments. So, you know, this is encouraging because it suggests we might be able to reliably do that if we have some small number of shots from the reactor, possibly like calibration shot that are like lower power. So this is one way people are trying to use artificial intelligence to help predict behavior in plasmas. Another kind of AI topic is around control. So TCV is a tokamak in Switzerland. And last year they had a Nature paper looking at using reinforcement learning to control the shape of plasmas. So they basically used an actor-critic architecture to learn how to optimally control the magnetic coils on the device to achieve specified evolution of the plasma shape. So they actually, you can see that there's kind of dots around this boundary. So the dots kind of specify the desired boundary shape, and the RL algorithm has to learn how to produce that evolution in shape. And they did this entirely using simulation, and managed to achieve like really good agreement in experiment. They even managed to produce some exotic plasma shapes that hadn't been produced before. So they call these droplets, and effectively they managed to produce two separated plasmas inside the device at the same time. And this isn't a purely academic thing. This could conceivably be useful because there's ways of starting up the plasma by effectively throwing two blobs of plasma together. It's called a merging compression startup. So this might actually be useful. So again, this has kicked off a lot of interest in using reinforcement learning in control for fusion reactors. Another control-related development that's a few years old now is something called Google Optometrist. So reinforcement learning is great if you can kind of clearly define what your success metric looks like. So if you have a clearly defined reward function, sometimes you don't have a clear idea of how to write down what good looks like. So particularly in fusion reactors, there's lots of different performance metrics that you might want to optimize. There's engineering constraints on the machine that you might be more or less averse to getting close to. And so sometimes it's hard for an operator to say what's better. They just kind of know it when they see it. And so Google set out to build a kind of algorithm that allows you to explore the parameter space, taking input from operators on how to progress. And that they called it optometrist because it basically presents the operator with a reference and a new case and allows the operator to say which one of those two things is better. And this is meant to be kind of similar to how an optometrist tests which glasses you need by showing you different lenses and asking you which one's better. They did this in partnership with a private fusion company called Tri-Alpha Energy. And they describe this situation as trying to optimize a hidden utility model. So there is some kind of underlying model of what good is, but you don't have explicit access to it. So the algorithm is kind of summarized here. So you start off with what they refer to as meta parameters, but that's effectively like a reduced dimensionality parameter space. So it's the parameter space you're trying to explore. And you start by choosing a reference, and then you kind of go through this loop where you kind of take a step in this parameter space and use that to construct a proposal. You run the plasma with this proposal and then show the operator the kind of comparison between the results of this proposal and your reference. And then based on whether the operator thinks the new shot is better, worse, or as good as the reference, you update the reference settings. The other kind of aspect of this algorithm is that how aggressively it explores the space is dependent on how well it's been making proposals. So if the operator keeps accepting new proposals, it will take larger steps in the parameter space. Whereas if the reference is starting to be preferred regularly, it will realize that it's kind of found a local maximum and kind of take smaller steps to kind of explore that local region. We're not actually Tri-Alpha Energy actually managed to find a new, better parameter regime than the one that they've been than their previous best using this algorithm. So one which had a smaller rate of energy loss. We're not exploring the use of this at the moment, but I do think that the notion of using data science techniques to kind of optimally explore parameter spaces is very interesting and something that will be really, really relevant. The last thing I wanted to say is around data. I've only got one slide on this, and that's not to suggest that this isn't a really important subject. It's just a subject where I'm not so well informed. So one of the key points here is that ITER will produce around 2 petabytes of data per day. So that will move fusion squarely into the kind of domain that experiments like the Large Hadron Collider operate. And so data storage and curation will become very important, particularly if we want to be able to do, routinely apply machine learning approaches to large data sets. There's an increasing drive within the fusion community to ensure that the data we produce is fair. So FAIR stands for findable, accessible, interoperable, and reusable. And also to work towards having like common ontologies and standards to enable data sharing between different communities. A colleague of mine is actually giving a talk on this subject next Tuesday at an AI for Good meeting. So if this is something that's interesting to you, I can kind of point you at when that's happening. So kind of in summary, fusion has potential for near limitless, clean, safe, reliable energy. The only downside is it's very difficult to achieve, and there are still challenges that we're working on addressing to help move it towards kind of commercial viability. These include controlling plasmas and mitigating the effects of damaging instabilities, being able to handle and breed tritium, understanding material properties under high radiation doses, being able to eventually do complex multi-physics, multi-scale coupled engineering design, and also being able to develop maintenance challenges in hazardous environments. Despite those, none of these are kind of showstoppers that we're aware of. So we're moving forwards towards design of a prototype power plant based on the spherical tokamak concept, which targets operation in the 2040s and actual delivery of electricity to the grid. And the use of high performance computing, advanced simulation, and artificial intelligence allow us to extract the most information we can from the data we produce, both simulation and experimental, and to be able to look beyond what we can currently observe directly. I'll just leave you with a couple of quotes, one from the Rev Leberedian, who's a VP of Omniverse from NVIDIA, and one from Lev Artsimovich, who was the leader of the Soviet fusion program and one of the founders of the tokamak concept. And that's the end of my talk. Thank you very much for listening.
Thank you for that, James. We move on to the Q&A part of the talk then. Michael's been making a note of the questions that's gone into chat so far. So if I'll hand over to Mike to read those back to you, so that you can attempt to answer them where you can.
Thanks very much. The first question was from Mark Anderson. He wanted to know how radioactively contaminated the inside of the jet was. You said it was inhospitable to humans, but if it's radioactive and it's damaged, what happens to the material?
So I don't know a number in terms of the actual radiation that the kind of materials produced on jet. I know that there'll be kind of there's going to be a lot of work on decommissioning post-jet, and a lot of that will be around studying the tiles in jet that have been subjected to radiation damage to look at their properties. For a future reactor, it's expected that they will be radioactive on a timescale of about 50 years. So it's important to distinguish between radioactive waste on the kind of timescale that's produced by fission, where we're talking about hundreds of thousands of years. We're not talking about that with fusion. The reactor will be radioactive for about 50 years. So you basically kind of concrete it up, leave it 50 years, and then you can finish decommissioning it and open fine again. And that's if we can't develop new radiation hard materials in the meantime, which we're aiming to do. So yeah, so it's radioactive, but it's not radioactive on the same scale.
That's nuclear. Does that answer your question, Mark?
Yes, it does. I worked at Aldermaston in radioactive waste management, so hence my interest in it.
Thanks very much. I've got two related questions. One of them is, can the heat flux through the diverter be used for extra electricity generation? That's from Jeremy White.
Oh, yeah. So basically, I didn't really talk much about the kind of plant that goes around a fusion reactor, but the back end is all very much the same as a normal power station would be. So you would have coolant pipes running through the walls. They would have water in them, and the power deposition will generate steam, which will drive a turbine. So the back end of the reactor is really exactly the same as what any other reactor will look like. And so you'll have coolant pipes in the diverter region, and you'll use the energy that's deposited there for that. Most of the energy that's carried out is a lot of the energy that's carried out is carried by the neutrons as well, and deposited in the walls. So you have coolant there as well. But yeah, definitely make use of the energy that's deposited in the diverter.
And the other question was from David, is what mechanism are used to recover the heat energy? But I think you've answered that. Jeremy and David, are you both comfortable with that response?
Very happy, thank you.
Hi, Jeremy. We've got some questions now on the materials in use. Why not use 2 deuterium used for the fusion and get rid of the tritium? And the other question was, does fusion require a constant supply of lithium to make the tritium?
Good questions. So the deuterium one is because the DD cross-section, like the reaction rate, is 100 times lower for DD than it is for DT. So it's a lot harder. I think
Right.
personally that if nothing else happens, that would be the eventual goal far off in the future. You know, you would start with DT reactors, and then, you know, longer in the future, if no better alternatives come around, you'd research moving towards being able to do fusion with just DD. But it's harder, so it's not what we start with.
Sure.
What was the other question? Oh, it was the lithium. Yes,
Yeah.
you need lithium. So yeah, basically you need so really the fuel is actually deuterium and lithium. You need deuterium from seawater, and you need to mine lithium to put in the breeder blankets to generate the tritium.
Cool. Manuel and Sam, are you both happy with that response?
You are.
Yeah. Thank you. Sam? Yeah, thanks. Oh, sorry. Sam responded in the message in the chat. The other question was from Ashok, which is, what material is Tomahawk made of to tolerate plasma's temperature, and what is the useful life period of a Tomahawk?
So jet is made from, well, the first wall is made from beryllium for most of the vessel, and tungsten in the diverter. So tungsten has very high melting point and high heat capacity and conductivity as well, which make it good for dealing with the heat exhaust. I think for reactors, they're targeting kind of component life cycle replacement times of a couple of years. I think if you can't achieve that, then you're getting into dangerous territory economically, because it'd just be too much. The plant availability would be too low to make it economic.
Thank you.
So kind of interesting side, well, maybe interesting side note for that. The wall of jet used to be made of carbon, and they replaced it with metal wall because they found that carbon absorbs too much tritium, so it becomes a kind of regulatory hazard.
Right. Okay, cool. There's a follow-on question from Mark, is what do you need to do, and how do you test the computer-based theories against physical factors to ensure accuracy?
Yeah,
I think you may have covered that.
I'm not sure I actually did, and it's a good question. Okay. So I think, you know, you basically have to validate extensively against experiment, right? And you know, so while we don't have access to all of the conditions that are present in reactors, we do have, you know, we have experiments at lower temperatures and densities and lower neutron fluxes and things, and so we can use those to validate models to some extent. There's always a risk of what people call black swans, so effectively unknown physics that comes into play in the new regime. How you deal with that and how you do uncertainty quantification around that is really tricky. I've asked several people that question: how do you deal with epistemic uncertainty, like the unknown unknowns of moving to a new regime? And it's just a very difficult question. So basically, you know, we have good first principles understanding for some things. So, you know, plasma physics is really based on electromagnetism. The complexity is in the, so the kind of fundamental physics is well understood, but being able to predict all of the kind of complexity is numerically challenging. So people use reduced models sometimes, well, a lot of the time. And so you can kind of validate kind of reduced models that you're routinely running against higher fidelity simulations. But yeah, ultimately the biggest arbiter is validation against experiment.
Thank you. There's one long question from David Sinclair. It's ideally fusion would deliver a limitless supply of cheap energy, removing any dependency on fossil fuels and helping combat global warming. Or will it? With unlimited cheap energy, won't this encourage the human race to move to even higher levels of material consumption?
That's a very philosophical question.
It is a question, and I think I might invite David to unmute himself and chat to you about it.
So do I think that human civilization will move to ever increasing levels of consumption if we provide them with cheap, clean electricity.
And because if they do, is fusion truly a good thing? I think I'll let that.
I mean, I think the
take it from here.
alternative is that, you know, humans continue to consume, they just do fossil fuels instead and eventually kill themselves. I think, you know, I think solving the problem of climate change is, you know, I think the two are in some sense disconnected. You know, humans will change their behaviour however they will, and it's a question of whether we decide we want to solve the impending problem or not. That's probably not a great response to that question, but that's quite a hard question.
Dave?
Yeah, I don't think the question has an answer, really.
No.
But it's definitely a question that we ought to think hard about. Thank you.
Yeah, I mean, I think, you know, I would like to think that if you know, assuming human civilization survives the impending climate crisis, that it will take some message away from that en masse about, well, lack of thought when consuming.
Okay. And there's two kind of related questions. Another one from Jeremy. And the first is, do you think that fusion generation will be a few larger machines? Or do you think it will be many small machines when it reaches?
So I think in the short term, we'll probably end up with a smaller number of larger machines because larger is actually easier. Like, so this comes back to how effectively you can trap the heat. One of the easiest ways to get better fusion performance is just to make the thing bigger. It's more expensive, but it makes the kind of the fusion power easier to produce. So I think that will be the kind of the near term, but like any technology, as if this all comes to pass, as it matures, I would expect that you'll find ways of improving the performance with smaller devices. So I think my guess would be the trajectory would be starting with bigger things and moving towards smaller things. I might be wrong, that's kind of a speculation.
And thanks very much. And Richard asked a question, is do you think you'll be producing power before the completion of HS2? I would just ask Richard which leg of HS2 he was talking about. If it was the bit to Birmingham or the bit to Leeds. If it's the bit to Leeds, that's not going to happen.
I think it's generally my optimism about the way things progress in this country. I was drawn to the fighting Tamaraire in the background and thinking that by the time you get this working, it might all get towed away as an old technology. But that's perhaps me and my skeptical old age.
Good art identification over Zoom.
You did better than I did. I thought he was Turner, but I couldn't actually place it. Mark, to answer your question, answer your question about the recording. What will happen is in a few weeks' time, the BCS will publish it on our YouTube channel, and anybody that's registered for the event will get an email back from the BCS to say the recording is now available. You're welcome. Did anybody have any other questions? Did anybody want to unmute themselves and perhaps ask James a question directly, or anybody else on the panel?
Okay, well, I think we are running towards sort of the end of our scheduled time. So at this point, if I can hand over to Lisham from the IT to propose a vote of thanks, please, Lisham.
Thank you, Paul. Thank you. First of all, I'm Leshan from the local IET committee, so representing our team here in South Wales East part. So first of all, thank you, Dr. James, for the brilliant and informative talk. And I felt like in a positive way, sort of carried out a very short crash course on fusion energy. If you had a question paper at the end, I should have been, well, not sure how I'm going to do it, but that was really good. I mean, you started from the very, very small scale and sort of ended up doing sort of explaining in-depth information and so on. So that was brilliant. Thank you very much. And brilliantly handle all the difficult level questions and on the others as well. So well done on that one, James. Thank you.
Thank you.
Thank you. And Michael brilliantly handled all the Q&A sessions. So thank you very much for that one. and Paul, Michael, and Andy from the local BCS team. So putting all the hard work and sort of inviting James, sort of arranging the Zoom platform and everything. So thank you very much for all the efforts that you have made. It was great, and all the IET local committee team members sort of to spread the word around and to get people on board. So thank you very much for the committee members as well, and importantly, all you sort of attended today this particular session and making it great success. So thank you very much all for attending today's event. And as Paul mentioned, the recording will be available online probably in about 2 weeks' time. And also, Paul, I understand that there will be a feedback form going to send out at some point after that. Is that right, Paul?
Yeah, I think well, Michael can probably expand on that, because that's one of the areas he was looking at. If you want to say a quick word on that, Michael.
Yeah, fantastic.
There should be a survey coming out shortly.
Fantastic. So if you can sort of engage in that one and provide your feedback and so on, so that will help us to shape our future talks and all. And also keep eye on the IET website and the BCS website for our upcoming events and talks and all. And as we decided, majority of the talks will be hybrid or online. So there will be an opportunity for wider participation. So once again, thank you very much all for attending. James, fantastic talk. Thank you very much. And have a good evening all. Thank you.
You're welcome. Have a good night.
Night all.
Right all.
Thank you. Thank you.
Thank you. People are disappearing out of the meeting fairly quickly there, but yeah, I thought that was really good.
That's why I felt like, because he started very basic and that was really good.
Yeah,
that was a good one, Paul. So thank you very much. So we'll have a chat later on regarding a few other stuff. So thank you very much for organizing. That was a great success. Well done.
Yeah, and I'll pass the baton over to the IET for next year.
Definitely, we're looking forward to that one. So